Fluoroantimonic acid. Fluoroantimonic acid is a mixture of hydrogen fluoride and antimony pentafluoride, containing various cations and anions, the simplest being H2F and SbF6. This substance is a superacid that can be over 1,000,000,000 times stronger than 100% pure sulfuric acid, depending on proportion of its ingredients. It has been shown to protonate even hydrocarbons to afford pentacoordinate carbocations carbonium ions. Extreme caution needs to be in place when handling fluoroantimonic acid. It is exceptionally corrosive, but can be stored in containers lined with PTFE Teflon. Chemical composition. The reaction to produce fluoroantimonic acid results in formation of the fluoronium ion as a major species in equilibrium. SbF5 plus 2HF equals SbF6 plus H2F plus. However, the speciation of fluoroantimonic acid is complex and consists of a mixture of HF solvated protons, HF and H plus such as H3F plus 2, and SbF5 adducts of fluorides such as Sb4F21. Thus, the formula H2F plus SbF6 is a convenient but oversimplified approximation of the true composition. Nevertheless, the extreme acidity of this mixture is evident from the exceptionally poor proton-accepting ability of the species present in solution. Hydrogen fluoride, a weak acid in aqueous solution that is normally not thought to have any appreciable Bronsted basicity at all, is in fact the strongest Bronsted base in the mixture, protonating to H2F+ in the same way water protonates to H3O+ in aqueous acid. As a result, the acid is often said to contain naked protons, though the free protons are, in fact, always bonded to hydrogen fluoride molecules. It is the fluoronium ion that accounts for fluoroantimonic acid's extreme acidity. The protons easily migrate through the solution, moving from H2F+ to HF when present by the Grothus mechanism. Two related products have been crystallized from HF-SbF5 mixtures, and both have been analyzed by single crystal X-ray crystallography. These salts have the formulas H2F plus Sb2F11 and H3F plus 2Sb2F11. In both salts, the anion is Sb2F11. As mentioned above, SbF6 is weakly basic. The larger anion Sb2F11 is expected to be still weaker. Acidity. Fluoroantimonic acid is the strongest superacid based on the measured value of its Hammett acidity function H0, which has been determined for different ratios of HF, SbF5. While the H0 of pure HF is 15, addition of just 1 mol% of SbF5 lowers it to around 20. However, further addition of SbF5 results in rapidly diminishing returns, with the H0 reaching 21 at 10 mol%. The use of an extremely weak base as indicator shows that the lowest attainable H0, even with 50 mol% SbF5, is somewhere between 21 and 23. The following H0 values show that fluoroantimonic acid is much stronger than other superacids. Increased acidity is indicated by smaller, in this case, more negative values of H0. Fluoroantimonic acid 23 H0 21, magic acid H0 equals 19.2, carborane acid H0 18, fluorosulfuric acid H0 equals 15.1, triflic acid H0 equals 14.9 of the above. Only the carborane acids, whose H0 could not be directly determined due to their high melting points, may be stronger acids than fluoroantimonic acid. Sources often confuse the H0 value of fluoroantimonic acid with its pKa. The H0 value measures the protonating ability of the bulk, liquid acid, and this value has been directly determined or estimated for various compositions of the mixture. The pKa, on the other hand, measures the equilibrium of proton dissociation of a discrete chemical species when dissolved in a particular solvent. Since fluoroantimonic acid is not a single chemical species, its pKa value is not well defined. The gas phase acidity GPa of individual species present in the mixture have been calculated using density functional theory methods. Solution phase pKa of these species can, in principle, be estimated by taking into account solvation energies, but do not appear to be reported in the literature as of 2019. For example, the ion pair H2F plus *SbF6 was estimated to have a GPa of 254 kcal/mol. For comparison, the commonly encountered superacid trifluoric acid, TFO, is a substantially weaker acid by this measure, with a GPa of 299 kcal/mol. However, certain carborange superacids have GPa lower than that of H2F plus *SbF6. For example, HCH11 has an experimentally determined GPa of 241 kcal/mol. Reactions. Fluoroantimonic acid thermally decomposes when heated, generating free hydrogen fluoride gas and liquid antimony pentafluoride. At a temperature of 40 deg C, fluoroantimonic acid will release HF into the gas phase. Antimony pentafluoride liquid can be recovered from fluoroantimonic acid by heating and releasing HF into the gas phase. Applications. This extraordinarily strong acid protonates nearly all organic compounds, often causing dehydrogenation or dehydration. In 1967, Bickel and Hodgveen showed that 2HF*SbF5 will remove H2 from isobutane and methane from neopentane to form carbonium ions, CH33CH plus H plus CH33C plus H2, CH34C plus H plus CH33C plus CH4. It is also used in the manufacture of tetraxenon gold compounds. Materials compatible with fluoroantimonic acid as a solvent include SO2ClF and sulfur dioxide. Containers for HF/SbF5 are made of PTFE. Safety. HF/SbF5 is an extremely corrosive and toxic substance that is sensitive to moisture. As with most strong acids, fluoroantimonic acid can react violently with water due to the exothermic hydration. Heating fluoroantimonic acid is dangerous as well, as it decomposes into toxic hydrogen fluoride gas. The main method of containment involves storage in a PTFE container, as glass will dissolve upon contact. Safety gear must be worn at all times when handling or going anywhere near this corrosive substance, as fluoroantimonic acid can eat exposed flesh down to the bone while reacting violently with the water present in human cells.